So let's continue with example 2. All right. I let you guys to read this example. All right. So we plan to draw V and M diagrams without any equations, without finding the equations. Okay, based on what we learned before in example 1. Let's see if we can do it. So again, the first step, we have to find the reactions. That's easy, we can do that. We have reaction A and B. We use the equations that we learned before, and we find them. I did before. It's gonna be 5 pounds here, and it's gonna be 7 pounds there. I believe this part is easy, and all of you can do it. And then the next step is to find all the boundaries or break down this beam to different regions. So we'll start from the left side, and then whenever we see a change in loading, then it's a boundary and we have to draw the boundary. Okay. So unlike the previous beam, which had only 2 regions, this one has 4 regions, right? And then our X and Y axis, always we start from left, and let's say this is gonna be the X. Here, let's say this one to be V. And similarly, let's say this is V, and this is again X. So V, X, and M, X, right? So let's do it together and see if we can draw the V and M diagrams without actually writing any equations. So I start from the left always, and whatever loads that I see, if it's going up, then it means if it's going up, there is a jump upward. If it's coming down, there is a jump downward. So I have 5, so a jump of 5, let's say this is 5. Then, and we write down the numbers, so before we forget what numbers they were. And then nothing is going on, I stay at 5. And then remember, there is a jump of 2 downwards, right? So it means 2 units I'm coming down. I don't go to 2, I'm coming down 2 units. So it means now I'm at point 3, right? So that's another thing that I've seen a student make mistakes. So from the point that we are coming down 2 units. So it gets us to 3. And then everything is the same, constant, go there. And then 4 coming down. So it means now I'm at -1. Like this point, here is -1. So -1 going down there. And then what else? So 6 coming down. So if it is 6, it's all the way down here. So it means now I'm at -7, right? -7, because I was at -1, and then I had to come down 6 units. Now I'm at -7. And then all the way going down there to the right. And then at the end, if everything is correct, we should return back to 0. So that's another thing that we can check if we made a mistake, right? I have 7 and I jump up 7. So good, I started from 0 and I return back to 0. So everything is correct then. So that's our V diagram without actually writing any equations. Let's see if we can do that one for M. So first of all, when V is constant, like a line, a horizontal line, it means M is a line, either with a positive slope or negative slope, right? Remember Thomas pointed out in previous lecture, when we have a positive V, the slope on M must be positive, and when we have a negative V like this one, -1, the slope is negative. Let's see if it gives us those values. So all we need to do is at these boundaries to calculate the area, right? At the beginning, we are 0 because it's a joint. And remember, a joint always is 0. The only case that it's not 0, remember, when we have a beam, I'm just going to remind you, later we'll solve one problem. When we have a beam that, let's say one end of it is fixed. If one end is fixed, then at this point, remember, M is not 0, right? At this point, M is not 0. But whenever you see a joint like a pin here, like a point A on this beam, and or a roller like point E, they are 0. So no doubt. So beginning and end, then good. We have some information. We know they are 0. Later, when you saw something like that one, M is not 0. Okay, a fixed. So we need to find M for 3 more boundaries, like the one in the middle and the 2 sides. All right, let's see if we can do that. So what is the area? Oh, I don't want that one. What is the area here? 5 multiplied by 4, it's plus 20. So it is plus 20. Let me use another color. Cannot be seen easily. Plus 20. So if it is plus 20, then it means, let's say this is 20, somewhere around here, okay? And then the next area, so this one, if we calculate it, it's gonna give us 3 multiplied by 4 plus 12. So here I've seen a lot of mistakes that the students do. Should I put this point at 12? Or should it be at 32? Which one is correct?
32.
32. Thanks, Emily. Because remember, at any point that we are, the integral up to that point means the area from the beginning to that point, all right? From the beginning to the first boundary, the area is 20, so this point is 20. All right, so this is 20. All right, then to the next point, I add another 12. It means I'm getting to, let me write it down here, 32. And this guy is not correct, all right? Be careful not to make mistake. So let's move on, and then we need to be careful. This area now, all right, here is minus because it's below the graph. So minus what? It's gonna be minus 1 multiplied by 4, it's minus 4. Now we subtract 4 from 32, it gives us 28. You get to 28, maybe a point like that. And later when you draw that one, you don't need to be exact, but if you use like a ruler or a grid paper, it gives you maybe like some good indication. And then let's do a sanity check. By sanity check, it means let's see if we return back to 0. If I calculate this area, how much it is, let's say 7 This is 7, right? Remember it was 7. 7 multiplied by 4, 28, and it is minus. It is negative. Minus 28 plus 28, it gives us 0, right? So everything is correct. We return back to 0 and we are happy. So we start from 0, return back to 0. And we know all of these things are lines. So we just connect them by lines. So one line here, one line there, another line, and another line there. Let's see if Thomas and Aditi, they were right previously, because they said if this V is negative, then the slope must be negative. So we see, yeah, that's correct. Like here, V on the third zone is -4, right? And the slope is negative. Here is -28, like the V is negative, right? And the slope also is negative. When V is positive, the slope is positive. Remember always we have this formula, right? V is derivative of M. So it means the sign of V, we can guess the slope of M. And always M is integral of V, or area of V. Okay, so this is our V and M diagram without writing any equations. Looking at this diagram, so you can see M, maximum M is 32 pound-foot. And what is the maximum number you see on V diagram is 7, right? -7, but we just look at the, basically, the amplitude. V max is 7 pounds, okay? So we know if this beam is gonna break, where it's gonna break. It's gonna break at 32, and if it's gonna be sheared, which later I'll explain to you, it's gonna be on the last region over here, okay? All right, any question for this one? If you have a question, don't be shy, ask now, because it is important. You're gonna have one question like this in your exam, and you need to understand it well. Because the next topics, they all rely on this one. If you make a mistake here, if you cannot find these M max and V max, it means you cannot calculate the stresses, then you cannot find the area of the beam and so on. All right, so I'll take it as that you're good. Then let's solve another example together and see how we can draw the shear force and bending moment diagram. And by the way, these graphical method, like without writing equation, it's good to know it for your exam because you can check your solution, but always in the exam, we ask for the equations, all right? Later in future in your job, you can skip this writing equation, but sorry, now you have to learn how to use the equations, okay? So in your exam, we will tell you that write the equation, draw the diagram, and also check it that graphically to make sure that you haven't done it, you didn't do any mistake. All right, let's solve this example together. First, I'll let you to read it and think about it. Okay. Well, seems to be a complicated example, but let's see if we can solve it and if it is really difficult or not. So the only difference between this one and previous example is that we have a distributed load, but we are not worried about distributed loads, right? Because we know we can replace them with a concentrated load. However, there are some rules here which you need to follow. Okay. We go step by step. First step is finding the reactions. So we have a reaction at A and a reaction at B. And by the way, we know that the reaction at A has AX, but because AX is always 0, I just ignore that one, all right? So this AX, automatically we know it is 0. So we start with the free body diagram. Let me draw the free body diagram here for you on the maybe right side, because that figure is gonna get messy soon. So let's say that's the same beam. So we have the reaction at point A and reaction at point B. So this is, we call it A, and we call this one B. And then we have a distributed load, which I can take it and put back its equivalent, which is gonna be somewhere in the middle here. And the number is gonna be 10 multiplied by 6, right? 6 multiplied by 10 gives me 60. Let's keep all the unit in kilo, so kilonewton, and everything's in meter. And don't forget the distance, right here is gonna be, well, it's gonna be 3 meters. So here we have 3 meters. Okay, that's for that. And then we have this guy here. Let me move this one up. Then we have this load 10 over there. 10. All right, that's my free body diagram. And so from this free body diagram, I write down the equation here. We take the moment about point A equal to 0. So I have 60 multiplied by 3, and it is negative minus 10 multiplied by 8. B multiplied by 10 equal to 0. And from here, I can find B. Give me 26. Okay. Please check that I didn't do any mistake. So then sum of the force in Y equal to 0 give me A minus 60, and then plus B minus 10. And from here I can find A, which is 44. So far good, it's easy. We found A 44, I write it down over here, and we found B 26. Then we go to the next step, which is the boundaries. That's easy, we start from left. So one boundary there, right? So from there to the end of this distributed load, everything seems to be the same. So we put one boundary there because there is a change, and then there is one boundary there. And then at the end of the beam. All right, so basically we have 3 regions. All right, and we need to do 3 sections. We need to section this beam somewhere here. Let's call it S1, section 1. We need to section it somewhere there. Let's call it S2. And we need to section this beam somewhere there, S3. All right, and those points, they are just arbitrary points. Like, because when we have a like X, it means this X can be any numbers from 0 to 10 to the end. So that's one X. Okay. All right, so let's now do the section. I'll do the first section, S1. By section, I mean I cut the beam somewhere in the middle there, like S1, and I keep either the left or right side. But it seems it's wise to keep the basically the right side for this beam, right? Sorry, the left side. Let's do that. So So that's my section here. That's the beam. All right. So whatever I see there, so I see 44, I put 44 there. That's good. And then I see distributed load. All right. We need to just be very careful about these distributed loads. So this distributed load is, remember, on this region. Can I use this guy? Yeah. So somebody tell me what is the equivalent of this distributed load, right? Remember on this portion, what is the equivalent? Remember always we substitute a distributed load with its equivalent. What's the equivalent of this load that I'm putting there? It is 60 or no, something else? Any idea?
Would it be 10x?
Exactly. Thanks, Aditi. So it's going to be 10x, right? So the equivalent is going to be somewhere in the middle. But remember, we cut this portion of this distributed load. So it's not going to be the whole 60. It's just going to be a portion which is, the length is x. In other words, it's going to be 10 multiplied by x, because the length is x, all right? So always be careful. I've seen a student again make mistake. They put 60. 60 is for the whole things, but we cut only x portion of it. Remember, from the beginning to this point, it's x. All right. So since we keep the left side of this guy, and the left side, we know that it's going to be V and M, right? Let me replace those with the right colors so later we don't get confused. So this is the equivalent here, which is 10x. And here we have the V and M. M1, V1. All right? And so what is this distance? Probably you can guess, because the whole thing is x, that thing is in the middle. So then this distance must be x divided by 2, right? Like over here. So our free body diagram is complete. If we draw a correct free body diagram, the rest is super, super easy. We just write down. So remember, this is for section 1. So section number 1. So for section number 1, taking the moment about point S1 equal to 0. And remember, S1 is this point here, S1. So what do we have? We have M1, which is positive. Then we have 10x multiplied by its distance, which is x divided by 2. And then we have 44 multiplied by x equal to 0. So let me simplify this equation. M1 gives me minus 5x squared, and then 44x, right? So that's second order polynomial. That's M1. It's getting interesting, right? So, and then we write the second equation, which is sum of the forces in y equal to 0. In y, we have 44. Then we have minus V1. What else? We have minus 10x equal to 0. And it gives me V1 minus 10x plus 44. So we claim that always V is derivative of M. Let's see if it's really true. You see, yeah, it is. So always that's a good things to check. You take the derivative of M, you get V, it means everything is correct. So I suggest you, rather than just taking the derivatives, write the equation and just do a check to make sure everything is correct. So we are good now. V1, M1, we repeat the same process for section 2. Let's do it. For section 2, I'll keep this portion of the beam. All right. You may keep the right side. That's totally up to you. But I have a point to make here. So that's why I select this portion. So whatever we see here, I can see 44. All right. And then I have my load being distributed. Oh, all right. So remember, this time on the beam, the whole thing is being distributed, right? It's not just a section of it. And it is 60. So that's the point I wanted to say. Unlike the previous one, which was just a portion, it is this time the whole things. And this distance here is like 3 meters. It is very similar to the first diagram that we draw. All right. So be careful not to make mistake here. It's the whole things. The previous one is just X portion of it. It's the whole things. And then we don't have anything on this portion. So we get to the section. And at the section, we have V. And then we have M. M2, V2. All right. So we write down our equations again. I let you guys to do it. If we do it, it's gonna be sum of the moment about point S2 equal to 0. S2. And it gives me, all right, let's see. We have M2. We have 60 multiplied by the distance. Be careful about the distance. Remember, the whole things from the beginning to that point is X. This is one of those things that myself always I make mistakes. So from the beginning to here, we have X. So if the whole thing is X, then it means it's gonna be X minus 3. And then what else? We have 44 multiplied by X, and it is negative. 44 multiplied by X equal to 0. It gives me M2. If I do that, it's gonna be 16 or minus. Please always check my calculation. Plus 180. So guys, by the way, do you hear the background noise? Because it's a...
Every once in a while, yeah.
I guess it's a dump truck on Tuesdays. So if it's disturbing you guys, I can close the window. But if it's, okay, I guess they went. Yeah. Anyway, so V1, M2, all right. And sorry, we have M2 and we repeat the process. Sum of the forces in Y equal to 0, and we get to V2. I'm just gonna be lazy here and write down minus 16, take the derivative, but you can try it later. So that's V2. And eventually we got to the last part, but this time it's wise to take the portion on the basically right side, right? Again, if you are comfortable taking the portion on the left, that's totally up to you. You're going to get the same result. but I prefer the portion here. So I have 26 over there, 26. Then nothing except the V and M, which V for the right side is always going up, and M always is going to be clockwise. So it's going to be then M3 and V3. All right? So this portion is easy because there is nothing there. If we use our equation, we are going to find out that M3 is 26 and minus 26x plus 260, and V3 is going to be minus 26. Right? Please write down the equation later yourself and see if you get the same values for V3 and M3. All right? So just be careful about the distance. This time the distance from the beginning to this point is X. So from here, no, let me draw it somewhere down there. So from here to the portion that we cut is X. Always X start from the beginning on the left side. I keep repeating these things because I know it's easy to make mistake. Right? And then this distance, therefore, is the whole thing's minus X, right? The whole thing is 10 meters. So this distance is then 10 minus X, right? Be careful about that. So I'm highlighting it, right? So no matter where you do the section or which side you pick, left or right, the always our coordinates start from left and up to the point that you section is X. So we found V and M equation for this one. The only difference now between this equation and previous one is that they are second order. Like M1 is a second order polynomial. So it's more like a curvature shape. Okay. Let's draw them because the question asks us to draw this equation. Okay, I'll go to the next page. But before I move forward, is there any question? No? We're good? Okay, let's then draw the free body, the diagrams for this one.
I'm sorry, I have a quick question. So what if the beam was inclined? Would that make any difference? Like it would make it more complicated, I guess, but inclined on an angle?
No, that it's going to be for stresses when later we calculate. Yes, it's going to be a different. So Mohammed is asking, what if this beam, instead of being horizontal, is, let's say, is on an angle? It is a topic more for, we leave it for Mech 360, but the concept is the same, except you involve some angles there. Then this V is going to be on an angle, which you have to find these different components of that. It's just more complicated, more work, more math work, but the solution basically is the same. But in Mech 260, no, you're not going to deal with a beam which is on an angle, like an oblique beam. It's always horizontal beam, right? Or a vertical beam, because if it's a vertical beam, you just flip your page like 90 degrees. That's all, right?
Yeah.
So let's draw then the diagram for this one. Let me, because I'm going to the next page, let me write down my equation one more time here. So V1 was minus 10x plus 44, V2 minus 16, and V3 minus 26. This is the V, guys, and then M1 minus 5x2 44x, M2 minus 16x plus 180, and M3 minus 26x plus 260. All right, so let's move to this clean page. All right, so we want to draw these things, okay? And this is something that most likely you've learned it in one of your math or maybe in high school. So again, I draw the boundaries. All right, and then I draw my V and M axis. So it's gonna be this is V and this is M. V, X, M, X. All right. So our plan is to draw these things, right? So V1, it's a line, minus 10x plus 44. And for a line, we know that we need 2 points. X equal to 0 gives me V1 44, and X equal to boundary 6 give me 16. V is equal to 16. Right? So I just put 2 points, x0 and x6 for this boundary. So when x is 0, v is 44. Let's say this point is 44. And when x is 6, like this boundary in the middle, then v is 16. So 16, maybe a point, oh, minus 16, right? So this is minus 16. So let's say minus 16 is there. Are you guys with me? Please let me know if you cannot follow at any point. So it is minus 16 then. So this point, minus 16. All right? So, and these two, they're connected by a line because that's the equation of a line. So from there, I'm coming down there. All right? And by the way, we can also, you know, guys, let me close my window because there's a lot of noise. It's quiet, but it's gonna get hot, but I prefer quiet. Also, you can check that we found the reaction here to be 44 and this 126, right? We have them as something to double check. And remember what we said previously at the beginning, we have a force of 44 and then there is a jump of 44 from 0 to there. But this 44, we found it from this equation. So it means they are all good. So the second one, V2, region 2, is just a constant number. It is minus 16, which again, another things that confirms that we haven't done any things wrong because you're just there. There is nothing going on and we stay there at minus 16. And then V3 is minus 26, right? Minus 26, maybe it's somewhere around here. So this point, this guy, not that, is minus 26. Minus 26. or minus 26. I write it down here, right? And which also again confirms what we learned before, right? We are here as at minus 16, then at the top we have 10 kilonewton. It means we jump down 10 units, so it gives us minus 26. See, all these things you can use to check that your solution is correct. And then at the top, you have positive 26, so you jump up 26 units. And you return back to 0, so everything is good. And the solution is correct, all right? So this is our V diagrams. The difference between this one and previous one is when you have a constant load, like this kilonewton per meter, a rectangular shaped load, V has a slope, basically. Let's do the same things for M1, M2, and M3. Be careful, M2 is a polynomial, right? It's a second order, it's not a line. So if it's a second order, you need 3 points at least, or 4 points. In your exam, try to find 3 or 4 points and then approximately draw basically, or let me move myself up there. Now I have room there. Okay. All right. So what we're saying is 3 points. Let's try that. X, and remember this equation is for the first region, right? Between x0 to 6. I put x equal to 0, it gives me m equal to 0. I put x equal to maybe the last point 6. Give me, if I put 6, gives me m 84. So let's put those points there. So at the beginning it's 0, and then it is 84. Let's say 84 is something around there. 84. I need maybe 1 or 2 more points. So let's put x equal to, in the middle, 3, right? 3, it gives me, if I put 3, 87. So 87 is a little bit higher, so I'm in the middle. Maybe this is 87. So this is the middle. And this is 87. So this is 87 or 87, I write it down, all right? So sort of I know that these 3 points, and they have to be connected by a graph shape, something like that, right? But I suggest find the 4th point as well, because right now you don't know if this graph is something like that, or maybe something like that. Both of these are correct. So it's better to find also another point, which I suggest we look at like not a random point. Maybe this point when V is 0, right? Here V is 0. See this point? It crossed the axis. Why don't we we are curious to know what is, when V is 0, what is M? So, but we don't know the X for this point, right? How can we find X for this point? Any idea? We know V is here is 0, but what is X at this point? Are you guys with me? So the question is, here V is 0 because the line is crossing x-axis, right?
Would be 4.4.
4.4. How did you find it, Uma?
I used the equation for V1 and solved for
Exactly.
solved it for when it's equal to 0.
Yeah, that's correct. So as Uman said, because we know the equation for this line, it is minus 10x plus 44, right? If I set it to 0, so V1 equal to 0 means minus 10x plus 44 equal to 0, give me x 4.4. So at this point, V is 0. 4.4, all right? So I put this 4.4 into the M equation because remember we were looking to see what is M at this point, 4.4. It gives me M 96.8. So which is sort of, let's say that point. Again, everything is just approximately. We don't want like exact shape of the graph from you, but at least something that it's more like it. So it's a second order, and we just connect this one like that. Try to do your best. So like what I'm doing there. Okay, that's the graph. This is the graph for M. Oops, not that one. Okay. So any question for this part? Are we good? All right. So one more time, these numbers, this one was 96.8 and this one was 87, right? And yeah, let's draw the rest. M2, we have the equation here. M2 is a line, right? This one I'm writing M2. If it's a line, I need 2 points. First point, which is x6, because remember M2 is for this region, second region. The beginning is x6 and is x8. So if I put x equal to 6, you guys try to find it. So it's going to be M2. Let me bring my calculator. All right. So 16 multiplied by 6 plus 180, this gives me 84. And when x is equal to 8, let's try that one. It gives me 52. All right, so 84 and then 52, which is, let's say it's a point around there. And it's just the equation for a line, right? We are drawing M2, it's just equation for line, not red. Oh, why did I do it with blue? So it's gonna be that guy. Let me guys try that one with red. Okay. So far we got to that point, and then the last equation M3. X equal to 8 and X equal to 10, right? It gives us M3 52 and it gives us M3 equal to 0. So 0, line, connect these two, all right, these graphs. And also we can check other things to make sure. For example, at the end, we return back to 0. That's good. There is no discontinuity in M graph. Everything match, which is good. Like here is 52, either using the equation for the second region or the third region. And at the end, we return back to 0. So this is our graph. You can also go further, check the area to make sure, but you don't have to because, yeah, but that's something you can do later if you have time, all right? And looking at these graphs, we can find out that M max, the biggest number that we can see here is 96.8 unit kilonewton meter. That's our M max. And where this M max happens, at x equal to 4.4. So this beam is going to break at that point. And also another good things that we can double check is we know that V is derivative of M, right? So if at the point M is maximum, it means V is 0. Because remember, how do you find the maximum of a graph? You take its derivative, right? If somebody take the derivative of M equal to 0, it means V equal to 0. So at M max, V must be 0. Must be 0. Which is 0, right? Because this is how actually we found this 96. And we see at this point V is 0. So everything is matched, the math is correct, the graphs are correct, and so on. So similar to this equation, to this problem is something that I expect from you to draw in your final exam. So if you can understand it, it means you are good and you sort of need to solve and practice more problems to master these topics. So before I go to the next example, is there any question? Okay, I take it as no. Now let's solve another example together. I'll let you guys to read it. So we want to find out the maximum bending moment for this beam. A simple beam with a distributed load, but it's a, we want to find out basically a general equation. The intensity of the load is W. Sometimes we show it by W, sometimes by Q, doesn't matter, right? So first step, we find the reactions at A and B. So let me draw the free body diagram next to it so the image doesn't get messy. All right. So this is A and this is B. So A, B. What about this distributed load? We know that we just need to get rid of it by replacing it with a nice concentrated load that we like, right? In the middle. And this guy is going to be W multiplied by the length, so WL. And we know it is in the middle. So like this distance has to be L divided by 2. We do our things, our equation, and we find out that A is equal to B equal to WL divided by 2. So that's a step, is easy. Also, it's obvious, right? If you have a WL in the middle, each of them is going to be half of that. So that's the first step. Next step is the boundaries, right? This one, the boundaries, one at the beginning, like this one. And then everything is constant, which is good. It means our last boundary is at the end. So I only have one boundary, which is a good thing. So I pick my X basically at the beginning, left side. So that's about it, X. And the good thing is only one section is gonna solve my problem, right? Because I have only one region. So I draw the free body diagram for one section, like that. I put the loads. I have that one there. So now you know, like this distributed load over here is going to be not the whole thing. It's going to be just W multiplied by X, all right? Because remember, we just use the X portion of these things. Like from here to here is X, where we did our cut. So if that's X, then this distance is going to be X divided by 2, and this one is going to be X divided by 2. So we keep the left section, and on the left section, according to what we agreed, we are going to have V coming down and M. So M and V. So far good. We write down our equation for this point. Let's call it S, like because we did section S here. Sum of the moment about point S equal to 0. What do I have? I have M, which is positive. I have Wx multiplied by X divided by 2, which is again positive. And then I have like this WL divided by 2 multiplied by the distance, which is X, equal to 0. It gives me M. Let me simplify it. So it gives us minus half of Wx squared plus half of WLX. So that's the equation for M, all right? So we found the equation for M. If I want to find out the maximum M, I need just to take the derivative, right? To find max M, you need to write down dm divided by dx equal to 0, right? Always in math, remember when you wanted to find out the maximum of a graph or a function, you just take the derivative. So let's take the derivative, gives us minus wx plus half of wl equal to 0. From here, x is L divided by 2. So it means the maximum bending happens in the middle of this beam. It was obvious. We know if you have this beam, it's gonna sag like maximum in the middle, all right? But we just wanna make sure the math also confirm it. And at this point, we know V is equal to 0, right? Because dm divided by dx, in fact, it is V. Okay. Also, I can find the equation for V either by writing the sum of the forces in Y equal to 0, or just by using dm divided by dx, which gives me V minus Wx plus half of WL. If we use this one also, we get the same result. All right. So in the middle, oops, not that one. In the middle, we found M is maximum, right? So I put this X equal to L divided by 2 in this M equation to find M maximum. And maximum is equal to half of W L divided by 2 plus half of WL L. If I simplify it, it's going to give me WL squared divided by 8. All right. And that's a good formula to remember. If you have a distributed load like this one, the maximum is going to be in the middle. And this is the maximum value for M. Right? You can use it as a formula later when you design a beam, a simple beam like that one. All right, our time is almost done. If you guys are okay, I'm gonna take another maybe 5 minutes and then we're done. So also later, please try to draw this V and M. Since now you have the equations, the V is gonna be like a line, something like that, right? You just draw this V equation that we found. And M is a second order polynomial. So second order polynomial, also with the knowledge that in the middle, M is maximum because V is 0 in the middle, right? And also we found that in the middle XL2, M is basically maximum. So this is our V and M diagram. V and this is M. And the maximum, remember, is WL squared divided by 8. Okay? And these graphs, like this portion is WL2 minus WL2. All right. Any question for this one? So you will see in textbook that many times when later we want to calculate the stresses for a beam like that one, we just say that the maximum stress is in the middle and we use just this formula, WL squared divided by 8. Now you know where it comes from, right? If you are good, as an example, as a practice, I want you guys to do the same things that I did for this beam, and it is again important. So it is a practice example. Find the maximum bending moment. Similar to the previous example that you saw this time, this is the beam. I will put the solution there later, but please, before checking my solution, try to solve it yourself and then compare it with my solution. When I put the notes for you, I'm gonna put this, put it with the solution. So that's a beam like that. And then our load is gonna be, this time, is gonna be a little complicated. It's gonna be a triangle. Right? So this is this time W, and the length of this beam is L. Is it clear? So this is what we want to find out. We want to find out the maximum value of M, and also we want to find out where it happens. Like we want to find out X. Be careful, it's not this time in the middle, because unlike the previous one, you can guess there is more load sort of toward the end of this beam, probably something there. Try to do it on your own and then later compare with my solution. Okay, is there any question for this practice example? We're gonna think about it. And lastly, so in 1 minute, I promise I'll let you guys go. So this is a bonus assignment. In the past, I let you guys first read it. Right? So we have this beam on this bridge, and this guy is using, like, is biking over that, right? His weight is W, and we have A, B, and L. This is the only parameters that we know. So this W is not in the middle, right? The center of gravity of this bicycle and this person is at point G, and W is the distances A and B. And also we have the knowledge that A is smaller than B. That's all we know. And we want to find out the maximum bending while this bicycle is moving along this bridge, right? So remember, this bicycle is not fixed at one point. Right now it's here, the next time is over there. So probably the maximum is changing every time. You want to find out the maximum of maximum. That's what you want to find out. In the past, I put it as a bonus assignment. And the bonus was that whomever could solve this one and submit it to me, they could spend like a day or half a day in my workplace. I work in a company, which later I'll explain you more. It's called FP Innovations. You can Google it later. And I do lots of cool experiment, like a beam, breaking beams, and not all these Mech 260 stuff, a lot of dynamic stuff like mechanism and testing stuff. And the bonus was the student could spend time with me like a day or half a day, depends on the time that they have. But unfortunately now it is COVID, right? So I figured the bonus, if you could solve it, is gonna be 2% adding to your final exam, extra 2%. Okay. And yeah, that's the deal. So think about it, and you have the time, all the time by the end of, by the last session, basically, to think about it. It's not really difficult, but try to see if you can think about it and then email your solution to me. All right. So we are good to go. Thanks for staying longer. Try to keep the time, but sometimes it takes longer. Anyway, so that's it. If you guys have any question, I can stay longer. If not, we just say goodbye. Don't forget your assignment 3 is due, I guess, this Monday probably. And yeah, that's it. And see you on Thursday, by the way. Somehow I forgot that today is Thursday. Today is Tuesday. Is there any question? We're good? So, all right, then I assume as a no, and all right, see you next time on Thursday.
See you on Thursday.
See you.